Good morning, everyone. Welcome to Tech, AI, and Beyond. Thank you for joining us today. We have an exciting episode ahead, packed with valuable insights, so please stay with us until the end as we dive deep into the latest developments in generative AI. Let's get started. Today, we are going to dissect what is arguably the single most important architectural innovation in the history of modern AI, the transformer, which was first introduced to the world in a groundbreaking 2017 paper titled "Attention is All You Need." All right, so here's our game plan for today. We're going to start by talking about something I call the wall of context, basically the huge problem that older models kept running into. Then we'll dive into the attention breakthrough, which is the genius solution that changed absolutely everything. From there, we'll see how that breakthrough unlocked the power of scaling, which led directly to the titans of the new era, the big models we all hear about. And finally, we'll check out the evolving AI landscape today and wrap it all up with the Transformer's incredible legacy. Okay, let's kick things off with Section 1, the wall of context. You see, to really understand why the Transformer was such a revolution, we first have to understand the problem it was built to solve. We have to understand the wall that the entire field of AI had hit. This brings us to a really core question. Before Transformers, the dominant architecture for handling language was something called a recurrent neural network, or an RNN. For years, these were the best tools we had, but they had a fundamental, crippling flaw, a real Achilles heel. So what was it? So how did an RNA actually work? Well, this slide visualizes it perfectly with the relay race analogy. It tried to process language a lot like how a person reads, one single word at a time. It would ingest the first word and create a mathematical summary of it, called a hidden state. Then it would look at the second word and combine it with that first summary to create a new, updated hidden state. This little packet of context, this baton, would get passed down the line, word after word after word. The key concept here is sequentially. But here's the thing, that sequential process was both its defining feature and its greatest weakness. It led to two massive problems. First, it had terrible short-term memory. As it processed a long paragraph, the memory of the first few words would begin to fade. It's a technical problem we call the vanishing gradient, but you can think of it like whispering a secret down a long line of people. By the time it reaches the end, the original message is completely garbled. So if a text started with "I grew up in France," by the time the model saw the word French a few pages later, that original critical context of France might be almost completely lost. The second, and arguably bigger issue, was the computational bottleneck. Because every step depends entirely on the previous one, you simply cannot process the text in parallel. In an era of massive datasets and GPUs built for parallel tasks, this was like trying to fill an Olympic-sized swimming pool with a garden hose. It was incredibly slow and put a hard ceiling on how powerful these models could ever get. So AI was well and truly stuck. It was trapped in this sequential prison, unable to scale up. The field desperately needed a new architecture, a new way of thinking that could see the whole picture at once. And that brings us to the breakthrough. So how do you solve this context problem? Well, the answer lies in a mechanism that did something truly radical for its time. It completely abandoned recurrence. It threw the whole idea of processing word by word out the window. Instead, the self-attention mechanism allows the model to look at every single word in the input text at the exact same time. And for each of those words, it calculates which other words are the most important for understanding its meaning. I absolutely love this analogy because it just makes the concept click. An RNN at a cocktail party is like someone trying to follow a conversation with earplugs in, catching just one word at a time. It's slow, it's clumsy, and you miss a ton of crucial context. A transformer, on the other hand, is like having superhuman hearing. It can instantly scan the entire room, hear every conversation simultaneously, and immediately zero in on what's most relevant. It's not a linear chain of information anymore. It becomes this dynamic, interconnected web of connections. Okay, so this idea of superhuman hearing sounds fantastic, but how does it actually work under the hood? It's not magic. It's just some really, really clever linear algebra. This system is called the Query, Key, and Value Model, and you'll often see it abbreviated as QKV. The fundamental idea is to take each word or token in our sentence and transform it into three distinct mathematical vectors, with each vector having a very specific job to do. First up, we have the query vector. You can think of the query as the word itself actively seeking information. It's like the word is raising its hand and broadcasting a question to the rest of the sentence. Hey, based on my meaning and my position here, what other words do I need to pay attention to in order to fully make sense? It's a request for context. Second, every word also generates a key vector. Now, if the query is the one asking the questions, the key is the label that helps provide the answers.
The key acts like a signpost or an index card in a library. It essentially advertises the kind of information that word contains. So you have all these queries asking for information and all these keys announcing what information they have available.
And finally, we have the value vector. This one is pretty straightforward. It holds the word's actual semantic meaning. So here's where it all comes together. For any given word, its query vector is compared against every other word's key vector. It's essentially a matchmaking process. A high degree of similarity between a query and a key results in a high attention score. That score then acts like a volume knob, determining how much of that other word's value, its actual meaning, gets blended into our original word's representation. By doing this for every word against every other word, you build up this incredibly rich, deeply contextualized understanding of the entire text, all at once. Okay, so that QKV model is already incredibly powerful. But the designers of the transformer took it one step further. They realized that a single attention calculation might only capture one type of relationship, like grammar. But language is complex. What about pronoun references or semantic similarities? So they asked a brilliant question. What if we could run this entire QKV process multiple times, all in parallel? And that is precisely what multi-head attention does. The model runs the entire QVK process multiple times, say 8, 12, or even more, all in parallel. Each of these parallel processes is called an attention head. And what's so amazing is that during training, each head learns to become a specialist. One head might get really good at tracking subject-verb agreements, another might learn to figure out what pronouns like it or they refer to. A third might focus purely on thematic relationships. The model then combines all of these different specialized perspectives to build a deeply layered and robust understanding of the text. And this right here, parallelism. This is the absolute game changer. This is the single biggest advantage the transformer has over RNNs. All of these attention heads, all of these QKV calculations are just a series of matrix multiplications. And you know what piece of hardware is designed from the ground up to do trillions of matrix multiplications per second? GPUs, graphics processing units. This architecture was tailor-made for modern hardware. It completely shattered the sequential bottleneck of RNNs and blew the doors wide open for training models at a scale that was simply unimaginable before. This massive leap in computational efficiency didn't just lead to faster models, it led to a profound discovery about the nature of intelligence itself. It revealed the existence of scaling laws, and with them, gave birth to the large language model, or LLM. So, once researchers at places like OpenAI and Google had this incredible new tool, this highly parallelizable transformer architecture, they started to experiment on a massive scale. They trained hundreds of models of varying sizes, on varying amounts of data, with varying amounts of compute power. And as they plotted the results, they found something truly remarkable. They discovered a predictable, almost beautiful power law relationship. As you smoothly increased three key variables, model size, measured in parameters, the size of the training dataset, and the raw compute power used for training, the model's performance on language tasks would also smoothly and predictably improve. This was profound. It meant the path to more capable AI was, in a sense, straightforward. Just make everything bigger. It effectively turned AI research into an industrial engineering problem, kicking off a race to achieve unprecedented scale. But as this race to scale continued, something truly surprising and fascinating started to happen, something that wasn't entirely predicted by those smooth scaling curves. Researchers discovered what we now call emergent abilities. These are complex skills that are simply not present in smaller models. For instance, a small model might be terrible at two-digit arithmetic. Its performance is essentially zero. As you make the model bigger, its performance stays near zero. Then suddenly, once the model crosses a certain massive size threshold, it just gets it. Its ability to do math shoots up from near random to highly accurate. The leading hypothesis is that in order to get better and better at its simple goal of predicting the next word, the model is forced to build an internal world model, a deeper, more abstract understanding of the concepts behind the words. And these abilities emerge as a side effect. And it's this powerful combination, the efficient transformer architecture plus the discovery of scaling laws and emergent abilities, that gave birth to the AI titans that have now captured the world's attention. The Generative Pre-trained Transformer, or GPT series from OpenAI, is the perfect case study of these scaling laws in action. Each new version was a monumental leap in scale that unlocked entirely new capabilities, turning science fiction into reality. This timeline really tells the whole story. In 2019, GPT-2, with its 1.5 billion parameters, stunned the world with its ability to write coherent paragraphs.
It was so novel that OpenAI initially deemed it too dangerous to release. Just a year later, in 2020, came GPT-3, a 100-fold leap in size to 175 billion parameters. This is where those surprising emergent abilities began to shine, and its API access sparked an explosion of AI-powered apps. Then, in 2022, came ChatGPT. This wasn't a brand new model, but rather a new way of interacting with one, fine-tuned with a technique called reinforcement learning from human feedback, or RLHF, which taught it to be a helpful conversationalist. And in 2023, GPT-4 arrived, even larger and crucially multimodal, able to understand images just as well as text.
As you can imagine, the immense success and public fascination with the GPT series triggered a new global AI arms race. This has spurred on a whole new wave of competitors, many of whom are taking very different philosophical and technical approaches. To really understand this evolving landscape, let's compare two of the most interesting new players, xAI's Grok and the Paris-based startup Mistral AI. They represent two fascinatingly different strategies in this post-transformer world. This table does a brilliant job of illustrating these diverging strategies. OpenAI continues to pursue its core philosophy that maximum scale is paramount, creating the largest models and keeping them closed behind an API. Then you have xAI's Grok, which is trying to differentiate itself on personality with a rebellious voice and on timeliness by integrating real-time data from the X platform. And then you have Mistral AI, which is championing a philosophy of efficiency and openness. They are creating highly performant open-source models that can rival closed models many times their size, which is helping to foster a more decentralized and collaborative AI ecosystem. So, after this deep dive from the problems of the past to the competitors of today, what is the crucial point we should take away from this revolution? What is the core legacy of the transformer? When you boil it all down, it really comes back to that one core mechanism, that single, elegant idea that unlocked everything that followed. And this right here, this is the legacy. The transformer architecture, powered by that brilliant self-attention mechanism, solved the context problem that held back older models. But just as importantly, it solved the parallelism problem. This breakthrough enabled the discovery of the scaling laws, which gave us the direct recipe for creating the powerful large language models that are now reshaping our world. It was the key that finally turned the lock. So let me just quickly recap the most critical points from our journey today. We started by seeing how older models, like RNNs, were fundamentally held back by their one-word-at-a-time, sequential nature, which led to poor memory and a computational bottleneck. Then came the game-changing breakthrough, the self-attention mechanism, the core of the transformer, which let models see all the data at once, unlocking massive parallelism and a true understanding of context. This computational freedom led directly to the discovery of the scaling laws, the recipe that told us bigger is better. This, of course, fueled the rise of today's LLM titans like the GPT series. And now, that success has spawned a vibrant and competitive landscape, with philosophically different models like Grok and Mistral pushing the boundaries in new and exciting directions. Be sure to tune in for our next deep dive, where we'll explore the ghost in the machine, AI as author and conversationalist. Thank you so much for watching. If you enjoyed this, please subscribe, like, and share. And don't forget to hit the bell for more from Tech AI and beyond.